Hello, this is Bob Rutledge. In this second presentation, I will introduce the concept of optical calibration, in which the fluorescence intensity of an assay is quantified. Let me start with a short overview of LRE analysis. LRE originated from analyzing the kinetics of PCR amplification. This is done by plotting cycle efficiency against reaction fluorescence. Linear regression analysis is then applied to cycles within the central region of an amplification profile and is referred to as the LRE window. This generates values for Emax and delta E, from which Fmax is calculated. Target quantity is then determined by converting the FC readings within the LRE window into target quantity expressed in fluorescence units. The primary output of LRE analysis is thus an average F0 value that, depending on the size of the LRE window, is calculated from 4 to 8 determinations for each amplification profile. The next step in the development of LRE was to determine whether an average F0 value could be reliably converted into the number of target molecules. Anyone familiar with DNA quantification using a conventional fluorescence assay would be familiar with the approach used by LRE. That is, converting the fluorescence intensity generated by a sample into DNA mass based on the fluorescence generated by a quantitative standard, such as lambda genomic DNA. Although this is generally accomplished using a standard curve, LRE takes a simplified approach in which reaction fluorescence intensity is quantified, a process referred to as optical calibration. This generates an optical calibration factor, or OCF, that is expressed as fluorescence units per nanogram of double-stranded DNA. An average F0 value is then converted into DNA mass, referred to as M0. M0 is equivalent to the mass of the amplicon region within the target. The final step is to convert M0 into the number of target molecules. This is done by multiplying the number of base pairs per nanogram of double-stranded DNA and dividing by the amplicon size. Note that it is necessary to double this value for single-stranded targets such as cDNA due to the fact that the OCF is derived from a double-stranded DNA standard. How then is an optical calibration factor generated? This data set was produced during the early stages of LRE development. The main intent was to investigate the general effectiveness of optical calibration, along with determining the dynamic range of LRE. In this approach, lambda genomic DNA was serially diluted over a range of 7 magnitudes, and 3 replicate reactions conducted for each dilution. This produced a series of tightly clustered profiles reflective of the high level of precision that can be achieved as real-time PCR. Nevertheless, an obvious exception is a 2-molecule sample, which produced highly scattered profiles. As I will describe in the next presentation, the scattering is due to Poisson distribution and is not relevant to optical calibration. LRE analysis further illustrates the high level of precision that can be achieved in that both delta E and Emax show small variances over this large range of target quantities. The quantitative precision of LRE can also be assessed by converting the resulting F0 values into an optical calibration factor. If you recall, M0 is the mass of the amplicon region within the target. For lambda, M0 can be calculated by simply multiplying the nanograms of genomic DNA by the amplicon size and dividing by the genome size of lambda. The resulting OCF values are very similar across the 5 magnitudes of target quantity, generating a CV of plus or minus 16%. It is important to note that this CV reflects the precision that can be achieved with LRE analysis over a large range of target quantities. The quantitative accuracy of LRE can be further examined by using the average OCF to convert each respective F0 value into the predicted number of target molecules. When compared to the actual number of target molecules, this generates an average error of 11.7%. It was during this early testing of LRE that a number of important insights were gained. The first was realization that real-time quantitative PCR can be a very precise technology. For example, work with lambda genomic DNA, as illustrated in the last slide, indicated that quantitative accuracy can be maintained down to at least 19 target molecules. Of even greater significance was the concept of conducting absolute quantitative PCR using an OCF derived from a single quantitative standard. Among other attributes, this would eliminate reliance on target-specific quantitative standards. In addition, this presents the possibility of standardizing absolute quantification by adopting a universal quantitative standard, such as lambda genomic DNA. However, the application of a universal standard requires that a number of assumptions be made. Foremost is the universality of amplicon fluorescence. The central premise for implementing a universal standard is that all amplicons generate similar fluorescence intensities. Based on work with a large number of lambda amplicons, the universal nature of cybergreen 1 fluorescence has been found to fulfill this requirement. For example, amplicons differing in size, or GC content, have been found to generate very similar fluorescence intensities. Although I will not attempt to present additional details about this work, I would like to provide an example of this approach, taken from the testing of 2 high-performance lambda amplicons. This slide summarizes the optical calibrations produced by 3 different lambda amplicons. The data was taken from 8 runs, conducted over a 4-month period, with the data from each individual run presented across each respective row. It was concluded that there were no substantive differences in the fluorescence intensities produced by these 3 amplicons. This was based on comparing the average OCF from each of the 3 amplicons, which produced a variance of plus or minus 12.1%. Although the subject of assay performance is complex, this dataset does provide examples of how the general performance of an assay can be examined. One of the major objectives during the early stages of LRE development was to examine the precision of LRE analysis, particularly run-to-run variation. Data from the 8 runs presented here provides a nice example of how this can be approached. Foremost is the standard deviation of Emax, which is a major determinant of quantitative variance. Depending on the optical precision of the instrument and the number of technical replicates conducted, run-to-run standard deviations of plus or minus 1.5 to 2.5% are typical for Emax. In general terms, this translates to a quantitative variance of about plus or minus 15 to 25%. While providing a detailed description is beyond the scope of this presentation, work on primer design optimization led to the creation of 2 high-performance amplicons called Cal1 and Cal2. In addition to their role in optical calibration, these amplicons present the prospect of developing performance benchmarks that would, for example, facilitate evaluating differences in enzyme formulation, cycle regime, or instrumentation. Nevertheless, the most important determinant of assay performance is quantitative accuracy, a subject that is addressed in the next presentation. To summarize, optical calibration allows target quantities to be converted from fluorescence units into the number of target molecules. By exploiting lambda genomic DNA as a universal quantitative standard, the need to prepare target-specific standards is eliminated. This also presents the prospect of standardizing absolute quantitative PCR by adopting a single, universally accessible quantitative standard. Adoption of a universal standard would also help the establishment of performance benchmarks. These could be based on Cal1 and Cal2, which have been found to be exceptionally reliable under a variety of assay conditions. Optical calibration also provides an indication of the quantitative precision that can be achieved with LRE, which for the datasets presented here ranges from plus or minus 12 to 20%, depending on the amplicon. However, optical calibration alone cannot easily resolve potential systematic biases in absolute scale, produced, for example, by different instruments or enzyme formulations. Developing methods for evaluating absolute accuracy were thus of great interest and is the subject of the next presentation. This completes the optical calibration section of the overview. As always, thank you for your interest.